Hi everybody. Well, in the last lecture we were talking about property 5 and we had discussed two results related to that. Now this result, property 5, is basically reminding us of the property that how trigonometric functions were reciprocals of the other trigonometric functions, right? So we use the property that cosec is actually the reciprocal of sine, or sine is actually the reciprocal of cosec, that property. We also used that cos is the reciprocal of sec, or sec is the reciprocal of cos, that property, to prove the two properties that how arguments get reciprocated under inverse trigonometric functions, that sine inverse 1 by x is actually cosec inverse x and cos inverse 1 by x is sec inverse x. Similarly, exactly in the similar manner, we are going to use the tan and cot are reciprocals of each other, this property, to prove our very third result in property 5. So, under property 5, let us prove the last, that is the third result, which says that tan inverse 1 by x, this is equal to, what is tan inverse 1 by x equal to? No, it is not always equal to cot inverse x, just like was the case with sine inverse x and cos inverse x. Sine inverse 1 by x was always equal to cosec inverse x. Cos inverse 1 by x was always equal to sec inverse x. But tan inverse 1 by x is not always equal to cot inverse x. It is equal to cot inverse x only when x is positive. If x comes out to be negative, suppose x is a negative real number, then 1 by x is also a negative real number. In that case, tan inverse of 1 by x is not equal to cosec inverse x, cot inverse x, it is equal to cot inverse x minus pi. So, pi gets removed from the quantity that you obtain and the new quantity happens to be the value of tan inverse 1 by x. Please understand one thing, the moment you take x positive, 1 by x eventually comes out to be positive, right? If you have x positive, 1 by x will be positive always. If x is negative, 1 by x will be negative always. Reciprocal of a negative number is a negative number, reciprocal of a positive number is a positive number. Why am I not taking 0? Why is there no case to be 0? Because if x is equal to 0, 1 by x is 1 by 0, which is not a real number. Until and unless the input of tan inverse is a real number, tan inverse of that particular input cannot be defined, because domain of tan inverse x is collection of all reals, right? But what is the domain of tan inverse 1 by x? Domain of tan inverse 1 by x is collection of all reals minus singleton 0. Because for x equals 0, 1 by 0 is not a valid argument. Is it understood? Therefore, if I have tan inverse 1 by x over here, 1 by x should be either a positive real number or a negative real number, but it cannot be equal to 0. So, obviously, this 1 by x is coming from collection of all reals minus singleton 0. 1 by x will be positive when x is positive. 1 by x will be negative when x is negative. That is why this branch is governed by x being positive and x being negative cases. Okay, the moment x is positive, 1 by x is positive, so all the positive real numbers are being swapped. If x is negative, 1 by x is negative, so all the negative real numbers are being swapped. 0 as it is you cannot take, 0 here also you cannot take, right? So this makes sense that 1 by x is coming from r minus singleton 0, which is a subset of collection of all reals, which is the actual domain of tan inverse function. Fine, and then you have this, cot inverse x is defined, isn't it? Cot inverse x is defined because x is coming from collection of all reals minus singleton 0. What does this mean? X is either positive real or negative real, x is not equal to 0. So, x is coming from collection of all reals minus singleton 0, which is contained in collection of all reals. And you know that what is the domain of cot inverse x? It is again collection of all reals. So, if x is coming from here or x is coming from here, cot inverse x is definitely well defined. Is it understood? From this quantity you remove pi and you get the answer, which is equal to tan inverse 1 by x if x is negative. Otherwise, whatever cot inverse x comes out, that is your answer for x positive of tan inverse 1 by x. Is it understood? Now, in order to understand why branch comes in here, why we don't get a single expression single expression on the right hand side corresponding to the value of tan inverse 1 by x. One reason is this only, that the domain of tan inverse is collection of all reals which can be partitioned into two sets. One is all the positive reals and all the negative reals. 0 as it is here puncturing out, for that my tan inverse 1 by x is not defined. So the moment you separate it, partition the complete real line minus singleton 0 into two sets, one is positive reals, one is negative reals, we eventually get two values as answers of tan inverse 1 by x. So obviously we are going to take this as case 1 and prove how if x is positive, then tan inverse 1 by x comes out to be equal to cot inverse x. And then we are going to deal with this case 2, which is going to tell us that how if you take x negative, in that situation tan inverse 1 by x comes out to be equal to cot inverse x minus pi. Is it clear? Let's begin with the first case, case 1. Case 1 I am saying I have to show that tan inverse 1 by x is equal to cot inverse x for every x positive. X is greater than 0 can also be written as x belongs to 0 comma infinity, strictly greater than 0, and x is less than 0 can also be written as x belongs to minus infinity 0. Okay. If I have to show tan inverse 1 by x is equal to cot inverse x for every x coming from 0 comma infinity open interval, in that situation I am going to just take one x coming from this interval and prove this result is true for that x. So suppose I have x coming from 0 comma infinity, that is this x is some x positive, some specific x positive. For this x I have to show that tan inverse 1 by x is cot inverse x. I have to show for this x. Now cot inverse x, if you see, cot inverse x is a function from collection of all reals to 0 comma pi open interval, right? If cot inverse x is a function from here to here, this is the domain and this is the range of cot inverse. What about the graph of cot inverse? Cot inverse, as it is written on the board, it is from the collection of all reals to 0 comma pi. So collection of all reals is the domain, 0 to pi 0 open. So if I just make this line dotted, and there is this line that is pi which is also dotted because pi is not included, and here somewhere is pi by 2. The graph of cot inverse is like this. This is your cot inverse x. This point is pi by 2. This is 0. Fine. If this is cot inverse x, please understand carefully, what about cot inverse of this x? If x is strictly positive, x is coming from here, then cot inverse x is strictly coming from here. What is this? 0 to pi by 2. Pi by 2 excluded because 0 is excluded. X is not equal to 0. Corresponding to 0, cot inverse of 0 is pi by 2. If I am leaving 0 and taking all the positive reals, then the answers are going to leave pi by 2 and take everything from 0 to pi by 2. Fine. So if x is coming from 0 to infinity, 0 not included, then cot inverse x is going to come from 0 to pi by 2 excluded. So for this x, cot inverse x will be coming from, you can see 0 to pi by 2 excluded. See, it's swiping all the real numbers from 0 to pi by 2 excluded. So if x is a positive real, if x is coming from 0 to infinity, 0 excluded, then cot inverse x comes from 0 to pi by 2 excluded. By the graph you can very easily see this. Let cot inverse x be theta. Suppose corresponding to this x somewhere coming from here, the answer that is produced somewhere in 0 to pi by 2 interval, open interval, is theta. The name of that answer is theta, that angle is theta. Then clearly that theta is in 0 to pi by 2. That's what we've written, the value of cot inverse this x. Now, if you recall a result again, that cot inverse A equals B if and only if cot B equals A, provided what happens? Cot inverse A equals B if and only if cot B equals A, provided what happens? Provided what happens? This A, which is the domain of cot inverse, or in the domain of cot inverse, or it is the output of cot, lies where? Collection of all reals. And B, which is the output of cot inverse or the input of cot, is going to lie in the restricted domain of cot or in the range of cot inverse, which is 0 comma pi open interval. Is it understood? The moment you see that here, if you take this to be A and this to be B, then A is definitely coming from collection of all reals, isn't it? Where is A coming from? X is actually coming from 0 comma infinity. X is a positive real number, but if X is a positive real number, it is clearly a real number. Be it a positive real number or a negative real number, first thing that I want is that A should be a real number. Clearly A is a real number. X is a positive real number specifically, but it is a real number. Set of all positive real numbers is a subset of set of all real numbers. So if X is a positive real number, it is definitely contained in the set of real numbers as well. So yes, A is coming from collection of all reals. If I talk about B, B is in 0 to pi by 2. Now 0 to pi by 2 is contained in 0 to pi. If an angle is ranging from 0 to pi by 2, clearly it is going to be less than pi also. Fine. So less than pi by 2 means less than pi. Therefore, if B is coming from 0 comma pi by 2, that means it is coming from 0 comma pi as well. And therefore, if A comes from collection of all reals, B comes from 0 comma pi, then cot inverse A equals B can be written as cot B equals A. The moment I have cot B equals A, again at this step, whenever we have landed ourselves at this step, what have we done? We have used our very property of trigonometric functions to use or to bring tan in picture, to bring the next function in picture, which is the reciprocal of this. Reciprocal of cot is tan. I can write this as 1 by x equals 1 by cot theta, which is tan theta. So you have 1 by x equals tan theta. This implies 1 by x equals tan theta. If 1 by x is equal to tan theta, what is my next argument now? Exactly same thing, but with a certain manipulation I will be using over here. Let me write that down now. This we don't require. We've used this. The result that I am wanting to use is somehow a copy of this only, but just cot reverse by tan. So the result says that tan inverse A equals B if and only if tan B equals A, provided A, which is sitting as the input for tan inverse or output of tan, is coming from the domain of tan inverse or the range of tan, which is collection of all reals, and B, which is the output of tan inverse or the input of tan, should come from the range of tan inverse or the domain of tan, which is minus pi by 2 open interval. If A and B satisfy these conditions, in that case tan inverse A equals B can be written as tan B equals A, tan B equals A can be written as tan inverse A equals B. Right now if you see, if I take this as B and if I take this as A, where is A coming from? Where is A coming from? You know that if x is a positive real, then 1 by x is also a positive real. For every x positive, 1 by x is also positive only. It cannot be 0, it cannot be negative, it is a positive real. So this is a positive real. Now positive real is definitely a real. Collection of all positive reals is contained in collection of all reals. So this is definitely coming from collection of all reals. It is actually a positive real, but positive reals are reals only. So this is a real number. Moreover, if I talk about theta, this theta was coming from 0 comma pi by 2. Now if I want my theta to come from minus pi by 2 to pi by 2, you can very clearly see that if this is 0, this is minus pi by 2 and this is pi by 2. If my angle is coming somewhere from here, the first question carrying 1 mark, if sine of sine inverse of 1 by 5 plus cos inverse x is 1, then find the value of x. Let's write down the expression. The expression is sine of sine inverse of 1 by 5 plus cos inverse x is given to be equal to 1. Clear? Now obviously if sine of something is 1, that means this something, that is sine inverse 1 by 5 plus cos inverse x, will be equal to sine inverse 1. But I know that 1 is nothing but sine pi by 2. So I can write this equal to sine inverse of sine pi by 2. And I also know that sine inverse of sine x equals x if and only if x belongs to the principal domain of sine, basically that is minus pi by 2 comma pi by 2. Principal value branch, which we say minus pi by 2 to pi by 2. So over here, because the angle is equal to pi by 2 lying in this interval, therefore sine inverse of sine of pi by 2 is pi by 2. Another thing that we are aware about is that sine inverse x plus cos inverse x is pi by 2, right? And therefore pi by 2 minus cos inverse x is sine inverse x. So I can say this to be equal to sine inverse of 1 by 5 equals pi by 2 minus cos inverse x, but pi by 2 minus cos inverse x is sine inverse x. Now you all know sine inverse is a 1-1 function. Sine inverse of an angle is equal to sine inverse of the other angle. That can only be possible if both these angles are same, which implies x is equal to 1 by 5. Since sine inverse is an injective or a 1-1 function. You have got the value of x, and that completes our discussion over the first question. Second says if tan inverse x plus tan inverse y is pi by 4 and xy is given to you as less than 1, write the value of x plus y plus xy. Okay. So you are given that tan inverse x plus tan inverse y is pi by 4. Now obvious step next is to apply the formula of tan inverse x plus tan inverse y, but for that we need the condition of x into y. It is given to me that x into y is less than 1, so clearly I will be applying what? Tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy. This is equal to pi by 4. How can I write pi by 4? Pi by 4 can be written as tan inverse 1, isn't it? Tan inverse 1 is pi by 4 because tan pi by 4 is 1. So tan inverse of an angle is equal to tan inverse of the other angle. When we know tan inverse is an injective function, means that x plus y upon 1 minus xy is 1, which implies x plus y equals 1 minus xy, which implies x plus y plus xy is 1, and hence the value of x plus y plus xy is coming out to be equal to 1. Next question we have, write down the value of cos inverse of minus half plus 2 times sine inverse of half. Now if you remember, there was a property which we did, which inverse trigonometric functions pull out the minus sign and which inverse trigonometric functions do not. So over here we know that cos inverse of minus x is pi minus cos inverse x. It does not gulp in the minus sign, it does not take out the minus sign, it actually brings a pi in picture, and that's what it turns out to be. So in here, if I have cos inverse of minus half plus 2 times sine inverse of half, obviously cos inverse of minus half will be by the property pi minus cos inverse half plus 2 times sine inverse half. Clearly I know that cos 60 is half, so cos of, this can be written as cos of pi by 3 plus 2 times sine inverse of sine 30 is half, so I can write over here sine of pi by 6. This is cos inverse. Now you should know that cos inverse of cos x is x if and only if x belongs to 0 comma pi, and as I just told you, sin inverse of sin x is equal to x if and only if x belongs to minus pi by 2, the restricted domain for sin inverse. Using this, you can clearly see pi by 3 belongs in 0 to pi and pi by 6 belongs in minus pi by 2, pi by 2. So eventually what you are getting is pi minus cos inverse of cos x, this will be x plus twice of pi by 6, right? This gives you 3 pi minus pi, 2 pi by 3 plus pi by 3, so it is 3 pi by 3 which is pi, and so the answer to your very query is pi. The value of this expression is pi. Next we have if tan inverse root 3 plus cot inverse x is pi by 2, find the value of x. Okay. Again, one property which is clearly evident to be used over here is something related to pi by 2 and something related to cot inverse x. We know that tan inverse x plus cot inverse x is pi by 2, and so obviously if I am given pi by 2 and cot inverse x, I would always be wanting to club them together to bring tan inverse x in picture. So obviously in here I would be writing tan inverse root 3 equals pi by 2 minus cot inverse x. Now obviously pi by 2 minus cot inverse x is tan inverse x. Tan inverse is a 1-1 function. Tan inverse of this is equal to tan inverse of this, which implies root 3 is equal to x, and thus the value of x is clearly root 3 because tan inverse is a 1-1 function. Moving on to the next question, we have write down the value of sine of this particular expression. Okay. I have sine of pi by 3 minus sine inverse of minus 1 by 2. Now as we just discussed, which inverse trigonometric functions gulp in the minus sign, which pull out the minus sign, or which bring pi in picture and come out as a resulting value. If I talk about sine inverse, you should be aware that sine inverse actually pulls out the minus sign. Sine inverse of minus x is minus of sine inverse x. Okay. If it does that, then this expression turns out to be what? Sine of pi by 3. Now it is sine inverse of minus half is minus of sine inverse half. Minus minus will be plus, and this is sine of half. Then it is sine of pi by 3 plus sine, this is inverse. Sine inverse of half can be written as what? Sine 30 or sine pi by 6. Sine inverse of sine theta is theta if theta belongs in minus pi by 2 to pi by 2 closed interval I just had written, and pi by 6 is very much inside the interval, closed interval minus pi by 2, pi by 2. And so I am going to have the next step as sine of pi by 3 plus pi by 6, which is what? Sine of, this is 2 pi plus pi, 3 pi by 6, which is sine pi by 2, which is 1, and therefore the value of this expression is nothing but 1. Moving on to the next question, for 4 marks we have this particular expression we have to prove to be equal to 2b by a. Let's begin the computation. Over here you can see one thing, cos inverse a by b, cos inverse a by b. I am going to take cos inverse a by b to be equal to theta, which obviously implies a by b equals cos theta. If I take this as my very first step, my LHS, my complete LHS which has to be proven to be equal to 2b by a comes out to be what? LHS is tan of pi by 4 plus half of theta, because cos inverse of a by b is theta. So this is plus theta by 2. Then you have plus tan of pi by This is pi by 4 itself, that's not pi by 2, it's pi by 4. Here it will be pi by 4 minus, now again this particular expression is equal to theta, so it will be theta by 2. Fine. This is what you have as your left hand side. You can see it's pretty simplified. Tan of A plus B is tan A plus tan B upon 1 minus tan A tan B plus tan of A minus B, tan A minus tan B upon 1 plus tan A tan B. Tan pi by 4 is 1, all of us know. So simplify this, you get 1 plus tan theta by 2 whole upon 1 minus tan theta by 2 plus 1 minus tan theta by 2 whole upon 1 plus tan, and this is theta by 2. Clearly you can take out the LCM as 1 minus tan theta by 2 into 1 plus tan theta by 2. A minus b into a plus b is a square minus b square, so LCM is 1 minus tan square theta by 2, that's the LCM. And here you have 1 plus tan theta by 2 whole square plus 1 minus tan theta by 2 whole square. So 1 plus tan theta by 2 whole square plus 1 minus tan theta by 2 whole square. This comes out to be what? A square plus b square plus 2 tan theta by 2 plus again a square plus b square minus 2 tan theta by 2 whole upon 1 minus tan square theta by 2. Clearly this gets cancelled out. Now that we have this long expression, in here you can see 1 plus 1 is 2, tan square theta by 2 plus tan square theta by 2 is twice of tan square theta by 2. So 2 comes out common, 1 plus tan square theta by 2 whole upon 1 minus tan square theta by 2. You know that 1 minus tan square theta upon 1 plus tan square theta is cos 2 theta. Do we know that? Yes. Cos 2 theta is 1 minus tan square theta upon 1 plus tan square theta. Basically the thing to be noticed is that if here it is 2 theta, here it is half of 2 theta, which is theta. So if here it will be theta, here it will be theta by 2. I am right now having 1 plus tan square theta by 2 upon 1 minus tan square theta by 2. Here if it was 1 minus tan square theta by 2 upon 1 plus tan square theta by 2, I would have got cos of twice of theta by 2, which is cos theta. And therefore this turns out to be twice of, this is actually reciprocal of 1 minus tan square theta by 2 upon 1 plus tan square theta by 2. So my answer will be 1 upon cos theta. So 2 is already there, 2 into 1 upon cos theta, which is 2 upon cos theta, using this particular formula. 2 upon cos theta, but cos theta is what? Let's see, cos theta was given as a by b, so this is a by b, which is 2b by a. We began with the left hand side by bringing in this manipulation in picture, and we proved it to be equal to the right hand side. Let's move on to the next question. We have with us, this particular expression is to be proved to be equal to pi by 4. Now these type of questions are pretty famous, you can see in the past year papers as well. What we do in here is we club any two. Let's club these two and then club these two, apply the same formula twice. Tan inverse A plus tan inverse B. I am talking about the computation of the LHS, my target would be to bring it to be equal to the right hand side. Tan inverse A plus tan inverse B is tan inverse A plus B 1 by 5 plus 1 by 7 upon 1 minus AB. Next you have tan inverse 1 by 3 plus tan inverse 1 by 8. So it is tan inverse, again plus is only there, 1 by 3 plus 1 by 8 whole upon 1 minus 1 by 3 into 1 by 8. Let's begin the computation. This is equal to tan inverse LCM is 35, you have 7 plus 5, that is 12 upon 35 whole upon 35 minus 1 is